In the previous video, we talked about the behavior of a function around a particular x value where we were addressing the non-removable discontinuities. So we might have a vertical asymptote there, and we looked on each side, and we had determined whether it went off to positive infinity or negative infinity based on the behavior as we took some number in the numerator and divided it by a little tiny number. And you'll remember that I actually went something like a positive divided by a tiny negative, got you negative infinity, and a negative divided by a tiny negative is positive infinity, right? So those were vertical asymptotes. In general, we're going to use that for the information in the succeeding videos, another chapter or two down the road where you might have vertical asymptotes. And so this behavior would be on either side of a vertical asymptote. But also what would happen is sometimes we had horizontal asymptotes, which said as you have some function, you become increasingly close to this horizontal asymptote. So this is asking about the behavior down here at infinity and negative infinity as you go farther and farther from the origin. So let's talk about this function. All right. So we know that it has an asymptote, a vertical one, at x equals -1 because that's a value that you cannot have in the denominator. It's excluded from the domain. And we could look at it. And talk about the behavior. And we need a number just to the left of -1. So that might be something like -1.001. So we would have 1 over -1.001 plus 1. We're just looking in generalities, not specific values. So this is 1, which is a positive number, over a tiny negative. So what that means is this is negative infinity. So on the left side of -1, whatever this function is doing, it's heading down to negative infinity on that side. The limit as x approaches -1 from the right. And I would need a number to the right of -1, so that might be -0.999 plus 1. This would be a positive number over a tiny positive, which is positive infinity. So what that says is over here on this side, it's racing off to positive infinity. Now, one of the other questions we would have is what happens to this function as we go off to positive infinity and to negative infinity. What is the behavior of the function there? So let's look at the limit as x goes off to infinity of 1 over, and let's not quite do, let's do this one, x plus 1. Now, what you're going to find is that there's a procedure for how to do rational functions where your limit's going to infinity or negative infinity. And then there's all sorts of variations, and then sometimes you just have to reason it out. But if you have something that is essentially a polynomial over a polynomial, then the technique you're going to use is to divide each term, top and bottom, by the biggest powered variable in the denominator. So you look it over, say, all right, I've got a polynomial on the top, and 1 is actually a polynomial that's a monomial. And then you're going to look at the bottom, and it's a polynomial. So we're going to divide every term by the biggest powered variable in the denominator, which is x. It's my only one. So I would have the limit as x goes to infinity of, now what I've got is x plus 1 and a 1, and I'm going to divide everybody by x. Okay? Now, what we know is if dividing by a little tiny number gets you a big number, taking a number and dividing it by a huge number is going to approach 0. So over here, now remember, this is going to infinity, so this is not like it's going to 4 or 40. This is going off to 400, 4,000, a million. So this is a 1 divided by a huge number. This is going to go to 0, right? X over x, anything over itself, is 1. And 1 over x is going to go to 0 because you're dividing 1 by a huge number. So what you have is the limit as x goes to infinity. You've got 0 over 1 plus 0, so this is 0. Right. Then let's do the limit as x goes to negative infinity of 1 over x plus 1. So the biggest powered term that's in the bottom is x. We're going to divide each term by x. And then we're going to reduce. This is 0. Anything over itself is 1. This is 0. So this turns out to be 0 as well. And when we get to graphing, you're going to use that to talk about its behavior as it comes down this way. It's approaching 0. Now, let's try some problems that are not specifically related to a picture. So I'd have the limit as x goes to infinity of 2x plus 3 over x squared minus 2x plus 1. And this is a polynomial over a polynomial. So we look it over. You look at the biggest powered term in the denominator, not the numerator, the denominator, and you're going to divide each term by that. So the biggest powered variable in the denominator is x squared. So you're going to have x squared minus 2x plus 1, and each one of these is going to be divided by x squared. Now, you can reduce this, but after you get used to this, you'll be comfortable asking yourself these questions. 2x over x squared is 2 over x. 3 over x squared doesn't reduce. X squared over x squared is 1 minus 2x over x squared is 2 over x plus 1 over x squared. Okay? So this is going to go to 0 as x gets very large. This is going to go to 0. This is 1. This is 0. This is 0. So it's 0 over anything is 0. Looks kind of like we're on a roll, but we're going to do one here in a minute that's not 0. Let's look at the limit as x goes to negative infinity of 3x squared plus 6 over 2x squared minus 1. Now, it's a polynomial over a polynomial, so we look it over, go to the denominator, find the biggest powered variable, that would be this x squared, and you're going to divide each term by that. So you divide everything by x squared. So here we go. 3x squared over x squared is 3. 6 over x squared is 0. 2x squared over x squared is 2. Minus 1 over x squared is 0. This doesn't look like a number at all. This is a 3 though. So 3 plus 0 over 2 minus 0 is 3 halves. Let's look at the limit. Now, in the previous example, you may remember something from college algebra that talked about your end behavior as x gets very large. And it had to do with the powers. And it was something along the lines of, if the power in the numerator is less than the power in the denominator, and they probably called it the degree. If the degree of the numerator is less than the degree of the denominator, then y is equal to 0 is your horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, then the ratio of the lead coefficient of the top to the lead coefficient of the bottom was your horizontal asymptote. So that is being supported by these limits. Here's a polynomial. The biggest power term on the bottom is x cubed. And depending on your teacher, they may let you just squeeze this in on the original problem. I let my students squeeze it in. It's a lot to write down. Gets kind of busy. So you're going to divide everybody by x cubed. So as you can tell, the dominant term, the one that's in front, is the one that sort of controls the behavior on the ends. Because it's the biggest power, it's going to grow the fastest and dominate the other terms. So what you would have is 4 over x cubed. If x is a huge number, this is going to go to 0. Minus 4 over x squared. Well, this x squared actually cancels 2 of these and leaves you 4 over x. This is going to go to 0. X cubed over x cubed is 1. 5 over x cubed goes to 0. 2x over x cubed is 2 over x squared. That's going to go to 0. 3x squared over x cubed is 3 over x squared. 3 over x. This is going to go to 0. And x to the 4th over x cubed is x. So what you have is x plus a bunch of zeros over 1 and some zeros. So this turns out to be x. This is not a number though. So technically up here, right, we're not substituting in numbers yet. We're still kind of talking about it. So this is sort of like what's going on, but we still haven't taken the limit yet because we're not substituting in a 4 or anything. We've got an x, okay? So as x goes off to infinity, the answer is infinity. So the limit as x goes to infinity of all of this is infinity. So way down there on the end, it's racing up to infinity. Let's do another one. So the biggest powered term on the bottom is 3x squared, and the biggest variable is x squared. So you would have your 3x squared minus 9x, 6x to the fourth plus 8x over x squared. So this is going to go to 0. This is going to go to 0. The top is going to be 6x squared. And the bottom is, I wrote that over to the side. And the bottom is going to be 3. Now, as x goes off to negative infinity, we'd have 6 negative infinity squared over 3. So 3 goes into 6 too. So this is technically 2 times a negative infinity squared. Now, negative infinity squared becomes positive, right? So technically you've got 2 infinity squared, but infinity squared just means it's an even bigger number because you took a big number and then squared it. And then multiplying it by 2 does not get you a specific value like 1,000 times 2 is 2,000 or 1,000,000,000 times 2 is 2,000,000,000. This is twice some huge number. So twice some huge number is still a huge number. So the proper answer is just infinity, not twice infinity. All right. Now, here's a couple that make you kind of have to think about it because they're not polynomials over polynomials. So if you're going to go off to infinity and you have a huge number squared, so let's say we made it down to like 10,000. Okay, so 10,000 squared minus 10,000 to the fourth, right? This is a big number. Okay, this is a big number. This is a big number, that same big number squared again. So this is going to be a negative huge number. So the limit as x goes off to positive infinity is going to be negative infinity. Let's try a couple more problems where you have to reason this out. So if we have the limit as x goes to infinity of the square root of 36x squared plus 3 over 9x minus 2. We haven't done one with square roots in here. The numerator behaves as if it's just the square root of 36x squared, because if you think about infinity and then you're going to square it and then you're going to multiply it by 36, adding 3 to it really doesn't change really an effective increase in value. So it's sort of extraneous, inconsequential. So we can just ignore the plus 3. The 36x squared, if you square root it, it's going to be 6x. Not the square root of 6x. And the 6 times infinity is 6 times whatever number you're thinking, but you're doing infinity. So it's still just infinity, even if there is a 6 there. So what we've got is we're going to treat this as if it's the limit as x goes to infinity of 6x over 9x minus 2. Now the biggest variable term that's in the denominator is an x variable. So we are going to divide everything top and bottom by that. So this is going to go to 0. The two x's are going to cancel, these two x's are going to cancel, and you have 6 over 9, which is 2/3. So the limit as x goes to infinity of the square root of 36x squared plus 3 over 9x minus 2 is 2/3. Now, sometimes it helps to know what things look like. So if, as a graph, so if I want to talk about x going off to negative infinity of e to the x over 1 plus x to the minus 1, this is the same thing as e to the x over 1 plus 1 over x. Now, I'm not dividing everybody by an x. X to the minus 1 is 1 over x. So I can go ahead and think of this 1 over x as we're going to infinity as this is 0. So I have limit of e to the x over 1 plus 0, which is e to the x. Now, what is e to the x doing? E to the x looks like this. So e to the x is, as you go to negative infinity, is getting closer and closer to y is equal to 0. So the answer to this one is 0, because that's what the y value is approaching as x gets farther and farther in the negative direction. And then this one's kind of a question that a lot of teachers like to ask. Once in a while I ask it, sometimes on a homework or on a test. But this one, let's talk about the cosine curve. So the cosine curve, very slanted axes there, looks kind of like this. And it bounces between 1 and minus 1. And it does this forever, and it never stops. Of course, it does this forever this direction too. Okay, so it never stops, and it's always just going between 1 and minus 1. So as x gets very large, as we're going this way, and we're heading off to infinity, the question is, as x gets very large, as I go farther and farther this way, is cosine approaching a single value, or is it heading off in a particular direction, like it's heading off to positive infinity or to negative infinity? And no, it's not. It just keeps bouncing around with every number in between minus 1 and 1. So this one does not have a limit, because the concept is we're either approaching a value for L, like 1/2, 0, 2/3, 142, or we're approaching a direction. We're ripping off to positive infinity or to negative infinity, but this one's not doing any of those. So the limit does not exist. The next video we're going to have is a trig limits video. And after that, I'll have a kind of cumulative review, a practice test that you'll be able to access and grade yourself. I'll put the solutions with it instead of just the answers so that you can see where the mistakes are, if you made any. And don't forget to look down in the description and see the link to the next video and to see the link to the practice problems for this topic.